Hi, Sumaya. Oh, right. So my AP lecture went a little longer than I thought. It just ended. So I just need to kind of clean up a little bit, and we'll start right at 11:10. That's 6 minutes from now. Okay. Thank you for those of you already tuning in now. Okay. What am I doing? Oh. Hey, Ali. Hey, Bruno. Bruno, that's the first time I've seen you here. Welcome to the stream. Thank you for the subscribe. Don't forget to hit subscribe and smash that like button. Okay. Labiba, good morning. Dennis, good morning. No exclamation point this morning, Aaron. Very atypical. Hi, Shelly. Good morning. Hey, Alton. Hey, Justin. Feeling better? Got your taste back? It's okay, Aaron. Don't worry about it. I'm just giving you a hard time. We're going to be starting in 2 minutes. Okay. Oh my gosh, Shelly, thank you so much for your dedication to the cause. Okay, yeah, I do, Shelly. I do. Thank you very much. I got 1 more minute. Thank you so much for your patience for those of you who have tuned in already. I appreciate it. Okay, and this shouldn't take too long, I think, right? So we're looking at probably 15 to 25 minutes of material today, right? While we're still waiting, be sure to text your group members. I know who they are, right? I know what groups you're in, and give them a heads up and tell them to, get your butt over here, right? The live stream's happening. And it's only like 20 minutes long, so hurry up before you miss it. Jeez. Hi, Esther. Hello. Elan. Good morning, Lars. Oh, where's Gallagher? I kind of miss giving him a hard time about Meridian 8. Hey, Ethan. All right, it's 11:10. We got 22 out of 68 of you in here. Hopefully the rest of you will catch it later. Let's get started, okay? Who's pumped? Let me see the pump emojis in the chat, all right? And there's only one pump emoji, okay? That's acceptable. The gas pump, okay? Good morning, Suborna. So good to see you, okay? All right, but let's get pumped up. And today we're talking about, here's a do now, all right? I should have put this up. Yeah. All right, if I have a current and I have a positive current going this way, where does the electric field point in this region? And where does the electric field point in this region? Hint, it's either into the page or out of the page, all right? There's your do now, all right? Where does the magnetic field all right, where does it point? Okay? I'll give you the answer in 10 seconds. You can draw this in your notes. You can think about it, all right? And I know for this kind of learning and even learning at school that it can be really easy just to think about it. And like if you get the answer in your head, especially if you get it quickly, you can be like, oh, no biggie, I don't got to write that down. You should know that writing things down is never about like telling yourself what the answer is, but it's been demonstratively proved to help with your memory. All right, like neuroscientists have, this is like a very well documented thing, right? So just write this down anyway. You don't even have to write that down. You can just draw it, right? Just draw this, and that helps with your memory. This is why a lot of your English teachers still have you physically write than type things out. I mean, I type much faster than I write, but the act of writing it down, we don't really know the mechanism behind it, but it really helps with your memory. Right? It helps you remember things better and conceptualize things and organize a lot of things. Hey, Dahlia. Okay, so the answer is if I use my right hand rule, okay, my thumb goes up this way. Oh, isn't that out of the page? Woo! And here, it goes into the page. All right? Before we move on, I just want to talk about how this do now would look if it was a negative charge, right? So if I have a negative charge going this way, what do you think we do? We use our left hand, and unfortunately this is my right hand, so we use our left hand. It's a backwards L because negative charges act backwards from positive charges, okay? And if I use my left hand, I'll see it actually comes out of the page here and into the page on the side. And so it works backwards, right? Because I got two. So you should know I have two different hand rules, right? I got this. This is talking about the force, the magnetic force on moving charges, and then this one, right? This one talks this one talks about the magnetic field due to moving charges, right? So this is about the field moving charges generate. This is about the force a moving charge experiences from another field, not its own. Okay, you got it. Okay. Okay. So let's talk about a very interesting thing here. Okay. If I have you guys ready? A positive current and it goes up. We've already done this. The field is here. And it goes into the page here. Things are about to get really funky, all right? Remember, this current's going up. I drew my wire really skinny. That's a problem. Let me see if I can kind of... The current's going up, okay? Now, I'm going to add a second wire. Oh, wow, that's a thick wire, huh? And this one also has currents moving. In this direction. Already then, I want us to be qualitatively thinking, what's going to happen to the field here? What's going to happen to the field here? The answer is the field here decreases. This will decrease. This will increase. Why? I want you to think about why that happened. Why is the field in this region going to decrease? Why is the field in this region going to increase? Remember, any point that has two magnetic fields on it, to find the actual magnetic field, you add the two different fields together like vectors. All right? I want you to think about that for around 20 seconds. Like, why is the field here going to decrease when I add the second wire with the current going up? Why is the field going to increase here? Yes. In this section, doesn't this wire, its own field has a bunch of vectors out of the page here and into the page here, right? And over here, if the field due to this wire is out of the page, that cancels out and works against that one, that field. And for when it goes into the page here, it'll add on to that and make that field even stronger, all right? But what we're going to study today is not really about how to add the fields of two wires. It's knowing how the wires affect each other, like the forces that act on wires. Okay? So, for that, remember, if I'm looking at the force on a charge, I never talk about its own field. I only talk about the field due to external charges. Okay? So if I have a positive charge and it's moving up, where is the force on that charge? Now I got to use this rule, right? So this charge is moving up, its field is down, into the page. So its force is to the right, the left, okay? So its force is going that way. Whoa. So that wire is attracted to the other wire. I'm going to link you a pretty cool video of this happening, okay? Or you can look up any video on YouTube if you just look at jumping wires. If you YouTube search jumping wires magnetic field, anytime you have a wire in a magnetic field and there's current in it, the wire will shift in some direction based on the field. How do I know the B field goes into the page? All right. Now, Justin, I don't know what the resultant field looks like. I do not know if what the resultant field looks like here or the resultant field looks like here. But when I'm talking about this charge and moving, I don't care about its own field, so I'm only looking at the field of that wire. And the field of this wire points into the page in this region, okay? So I don't care about the field due to that one because it never feels its own field, okay? No. All right, and let's do the exact opposite, all right? Let's look at the field due to this wire. Over here, it's out of the page. And over here, it's into the page, right? I'm ignoring the field due to this wire, all right? So I'm only looking at this wire, right? And just like this wire, on the left side, it has field coming out. On the right side, it has field going in, all right? Let's look at the force on a positive charge moving this way. This time, it has velocity up, but now field pointing out, so the force points to the right. This should make perfect sense due to Newton's third law. If this wire is going to experience a force pointing to the left, the other wire needs to have a force pointing to the right that's an equal and opposite magnitude. So what you do, what we've actually just derived is any two wires that have current going in the same direction will be attracted to each other. All right, and that's what you see. There's a very famous MIT YouTube video where I have two wires like this, and when they have current running in the same direction, and I turn on the switch, they just kind of go like that, and they just kind of, I missed you so much. Oh my God, I hate quarantine. All right, like stuff like that. Okay. Let's move on to the reverse situation. Okay. Oh no. At the end of the stream, I'm going to link a GoFundMe. Okay. Just kidding. Seriously, I know. Wow, I mean, it does kind of suck for me to always be spending my own money on this and stuff. I know I have it a lot better than a lot of other people who are out of work. So please don't. If you really, yeah, I'm really not asking for any money, nor your pity or sympathy, because a ton of people have it worse, and they need our help more than anything. Okay. Let's take a look at the situation where my current goes up, and now I have current going down. So now I have currents going in opposite directions. Whoa, right? So again, due to this wire, current's going out of the page. And on this side, current going into the page. all right? So this wire, where is the force going to point? Okay. The force points in. I mean, the field points in. This really hurts. Okay, the field points in, the velocity's down, so the thumb points to the right. So the force is out, okay? And likewise, if I look at the field due to this downward moving charge, right? On this side, it's in. And on this side, it's out, right? If you still need help conceptualizing this, you really need to review the curling right-hand rule or the left-hand rule for negative charges, right? And guess what? If I place a second wire here and its current's going up, a positive charge moving up with a field pointing in now experiences a force to the left. Right? So which means, and remember, these wires aren't getting attracted to each other, right? I'm saying in this situation, I'm looking at the force on this wire, and in this situation, I'm looking at the force on this wire. So what this means is these wires repel, right? So once I turn on the current and one's going up and one's going down, okay, then the two wires they'll repel, okay? Whoa! So that's just my spiel on jumping wires or moving wires. There is a way to actually calculate the magnitude of the force, okay? So to do that, I want to look at the force on just one charge. Or let's take a look at all of the charges, all right? So how many electrons or protons are really moving here? I don't know, but let me just call their, so basically the force on the wire is equal to the sum of the forces on all charges. So that's equal to Q1 VB plus Q2 VB plus Q3 VB plus Q4 VB. Why am I, and this is actually equal to Q1 plus Q2 plus Q3 plus Q4 VB. Why can I factor out the VB? Because I'm assuming this field is uniform. So every charge, whether it's here, 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 it experiences the same field. All these charges, since they're in a circuit, are all traveling with the same velocity as well, okay? So I'm just gonna call this Q, where this is the total charge that's moving, okay? All right, so if you look at QVB, all right, and I'm talking about a wire of length L, okay? This is a wire of length L in a magnetic field, right? Then I can, how fast is each charge moving really? It's the length divided by the time, all right? So this is Q L over T times B. But oh my gosh, Q, the total charge that moves and the total time it takes to travel the length of the wire, this is actually equal to the current. So this is your formula for the magnetic force on a current carrying wire. It is actually the current running through it times the length of the wire that's in the magnetic field times the magnetic field. Okay, so basically, if I have like a 3-meter wire, but the magnetic field only acts on this section, right? The L in your formula is only this little L, all right? Because this part of the wire isn't affected by the magnetic force, okay? I know, and this is basically all you need to do your worksheet. It's very short, but it's a very difficult problem. I'm not very. It's a bit more difficult, and we can review it a little bit later. We can go over it in a mini lecture tomorrow when we go over the solutions. But for those of you who haven't looked at it yet, I'm just going to offer a little preview. This is your homework is based on how a railgun works, and a railgun is I wouldn't really call it a gun. It's a cannon, right? You'll see them. We have some land-based railguns, but the majority of them, I believe, exist on battleships. And what it is, it's a cannon that launches a projectile using current and magnetic field. So without the use of any explosives or gunpowder. So it's a completely electric-powered projectile launcher, which is pretty cool. Why do I say completely electric when there's magnetism involved? Because the magnetic field is generated by like a solenoid or something, right? So it's generated by an electromagnet. So everything is basically generated by current. So please look at the worksheet, all right, and complete it tonight by midnight. And that's it for my thing. Be on the lookout. I'm going to send some videos too about the jumping wire. A lot, it depends on the railgun. All right. And are there any more questions before I go? Alton, I think the physics behind railguns are really cool, but the actual weaponization of physics I find very uncool. All right. But another way to look at it is there are non-military applications of like the physics behind railguns, which is cool too. All right. All right, cool. So L for the length and formula. Does the magnetic field just stop or decrease? Oh, I mean, Elon, this formula is only valid for uniform magnetic fields, right? There's a much more general formula that involves like an integral in calculus, where you're talking about dB and dl, or not dB, like b as a function of position times dl, and we're not getting there. Okay. Yes, exactly, Mr. Ross. Yay for non-militaristic applications of physics. Hooray. Correct, Ethan. Okay. Like, how can I be less than that? Because the L for the length of the wire is talking about just the length of wire that's under the influence of the magnetic field. Okay? All right. So if that's it, you have 12 hours to do the worksheet. Make sure you understand, while it's not optional, I'm not checking for completeness, right? I just want you to try. And if you really don't get it, all you got to do is ask a question and write that down too. Okay? Yeah, Dimon, you were a wait. Diamond Ninja, hello. Would it be possible for a magnetic field to launch a space? Depends on what space elevator you're talking about. Like, If the space elevator is an actual rigid structure that goes in outer space, there's no way we can make something that tall without it bending or buckling, all right, under like the rotational forces of the Earth. Okay, all right. So get pumped for tomorrow. All right, we'll learn more about railguns, or mass drivers as they're called, and I look forward to seeing you tomorrow. Make sure to smash that like button. I only got 4 likes. It's -1 for every one of you. And have a great day. Okay, bye.